Hello, I'm Andrea Abba from Nuclear Instruments. Today I will talk about the readout electronics of Loki instruments installed at European spallation source. Loki is a small angle neutron scattering device, and its electronic is a successful story of cooperation between the European spallation source, ISIS mu and neutron source, and nuclear instruments and KAIN. Uh, in this slide, you can see the Loki detectors. Today, we will focus on not on the full instruments, but just on the front-end electronics, the readout, and the detector elements. The full readout system of Loki is a complex union of several readout elements. We will start from the detectors that convert the neutrons in electrical signals. The readout is the element that convert the analog signals from the detector in the processed digital stream of data that is then converting events by a backend electronics that collect all this data from multiple readout device and stream via Kafka to a file writer, a data storage, and a data analysis tool. The Loki detector are about 1,000 of aluminum tube with inside each one 7 straw tubes that are boron coated detector. This detector is position sense. That means that can understand the on the x direction the position of interaction of the neutrons, and these detectors produced by the Proportional Technologies Inc. In Loki, we have 3 banks of detector. The first 2 banks are fixed. The last one can be moved between 5 and 10 meters. Here some picture of the detector while they are tested at the European spallation source with a radiation source. During this test has been measured the efficiency that is about between 50 and 60%, and the position resolution is about 6 millimeters up to a very high rate. It is about 400 kilowatts. And the rate capability is still high. In fact, we have about 15% of that time at 2.3 megahertz. The straw tubes inside have 7 sub-tubes to increase the position, the vertical position resolution. These tubes, in principle, to be read, require to be read on 2 sides, and so we need for a single aluminum tube 14 preamplifier and digitizer channels that because we have 1,000 aluminum tubes, 7 straw tubes, by 14s, it means that the number of channels is over 20,000, so it's too big. So at DISIS, they have an idea to make this circuit that you can see on the slide, that is a voltage divider that can reduce from 14 to 4 the number of channel required to read out, and so also the preamplifier to read out the tubes without any significant effect on the speed and the sustainable rate. So how does it work? The tube itself is like a resistor voltage divider. So if the signals arrive on a side of the tube, we have a signal that is bigger on a side in respect of the other side. If we connect the tube in this way, we can also calculate not only the X position, but also the Y position of the neutrons. In fact, if the neutrons arrive on the top left, for example, we have a big signal on A, a smaller signal on D, a smaller again on B, and then a very, very small on C. In the middle, we have the same signal on all terminal. So we can, from the making the ratio between A, B, C, D, we can calculate both X and Y direction of interaction of the neutrons. This is the preamplifier of Loki. It's been designed by Eric in ISIS, and this preamplifier is in principle a high bandwidth transimpedance amplifier. The gain is about 6 millivolt per microampere of current produced by the tube, and the power dissipation is quite low because it's less than 20 milliwatts per channel. This is some nice picture of the detector installed inside the vessel of Loki. The vessel on the right when it was at ISIS, and the vessel commissioned in October 2023 in ESS. Here the electronics. Nuclear instruments design the R5560, that is a 125 channels digitizers that has been designed to fit at best the requirement of ESS. Here a picture of the frontal panel and of the inside of the device. You can see that we have a lot of RJ45 connector on the front. They are not Ethernet connector. Yes, there is also the Ethernet because the device can be read with both optical links and Ethernet, but the Ethernet connector you can see in the low left side of the device. There are for the analog input. In fact, the R5560 has a differential input. This is an important impact on the cost of the cables. That in Loki we have 5,000 of channels, so we have a very high number, more than 1,000 of cables. That's the different. The cost of the Ethernet cable, the Cat6 cable, is much less than the cost of a standard coaxial cable. Moreover, once the signal is differential and we have shielded twisted pairs, the immunity to the noise is much greater with this kind of of cables. So the speed of the digitizer is under 25 megasamples with 14 bits. That is much than enough for the neutrons. We have hundreds of input IO digital signals, and inside of the device we have a powerful zinc processor. So the core of the device is the DRQ. The DRQ is a module inside the device. We have 4 DRQ. The DRQ manage the acquisition of 32 analog channels. On the DRQ, we have a system on chip, the Zinc 7035, and the readout, the IDC obviously, and the links, optical links to interact with ESS facility readout system. As I said, we have 4 DRQs. They are interconnected each other with fast 20 gigabit links, and an analog front end and RJ45 for the 128 input. In Loki, the R5560 are organized in banks. So we have about 30 modules. Each bank is divided in rings, and each rings connect multiple R5560, up to 4. So up to 16 DRQ per ring. The rings are read out by a master module that is a particular FPGA that is part of the backend of the ESS. With each one has 12 rings to read out the modules. So we have two optical fibers in both directions that make a ring and connect 16 DRQ each one at a speed of about 10 gigabit per second. This link distribute the clock, the timing, the control, and collect the data. All these links are generated by multiple master modules for multiple instruments inside the ESS infrastructure. At the end, behind this master module, we have 100 gigabit connectivity that streams data upstreams to the Kafka infrastructure and the Apex control system. As I said, ESS timing is distributed on the optical link. Also, the clock is distributed on the optical links because from the 8-10-bit encoding, we can recover the clock. Recover the clock means that we also need a PLL to clean up the jitter of the reconstructed clock, because when we reconstruct clock, we increase the jitter, and if we put a lot of boards in a chain, the jitter becomes so high that we cannot anymore lock the data with the clock. So we need a jitter cleaner. So the clocks from the input SFP is extracted by the core FPGA firmware core and is fed to an external jitter cleaner that is then reprovide the clocks to the FPGA. The FPGA clocks the ADC and propagate the clock to the next element in the ring. In ESS has been demonstrated that it is possible to achieve 10 nanoseconds timestamp resolution in distributing the clock. As you can see in this example, where several boards is triggering a digital input, and with an oscilloscope, it has been possible. It is possible to measure the skew between the different signals. About the firmware of Loki, this is a very, very high-level representation of the firmware. For in instruments of 5,000 channel, you can imagine that the firmware is much more complex of this. By the way, at least this is a simplification. We have an input shaper and an output peak holder. After the shaper, we have a trigger circuit. The trigger works on all the side of the tube, while the shaper shapes independently each side of the tube, A, B, C, D. So the shaper shapes the sample signal in digital, obviously, and then we make a sum of all the signals, and we'll go to look for the peak. When we find the peak, we sample the peak of the shapers, and on the back-end electronics, we can calculate the center of mass. So this is some real signals from Loki, working Loki systems. You can see the signal generated, the derivative of the signal. In black, we have the sum of the signal. And from the second derivative of the sum of the signals, so we can find the peak that is marked in yellow. Then this peak samples all the shaper's output, and from the ratio between A plus B and the sum of A plus B plus C plus D, we can calculate X. Y from the sum of A plus D divided the total sum, we can calculate the Y. So when we have the position, as I said, we can look at the shapers and extract the amplitude of each A, B, C, and D. The whole firmware, the full firmware of Loki, but not only on Loki, also of Bifrost, Miracles, CISPEC, and Vespa has been written in Sci-Compiler. Sci-Compiler allows scientists like the Dr. Davide Raspino in ISIS to independently write the full firmware of a 5,000 channels instruments without the help of an FPGA senior engineering. A scientist, a physicist, can easily understand how to use this programming language and design by itself the firmware of the instrumentation. The power of here some picture of the sub-modules inside the firmware. You can see the tree organization of Loki firmware and some of the sub-design. The power of Sci-Compiler is not just the accelerating and making easy the design of firmware, but also the possibility to in-system monitor and debug with side access channels. So it is possible, for example, to run the experiment using the optical links from ESS to configure and read out the fast data while at the same time connecting via Ethernet to the instruments. It's possible to access to the Resource Explorer, that is an inside signal inspector that we have inside the firmware, and monitor any signal inside the firmware. So on the web interface of the R5560, it's possible, for example, to see the signal from all the tubes, the energy spectrum, the reconstructed positions, statistics like the rate, and also one of the last feature added to the firmware is the pulse shape discrimination to discriminate neutrons and gamma and just keep neutrons in the experiment, and so it can reduce the background. Yes, with the monitor it's possible also to monitor in real time the pulse shape discriminator if it is working, and easy select the correct threshold for Newton. So, for example, this allows to avoid ESS software infrastructure to include all the part of debugging and just insert the part of fast readout and the configuration, and leave the debug of the signal directly on the instrumentation. So inside the Sci-Compiler has been implemented and make available for all instruments that use and will use any of the Sci-Compiler compatible digitizer. Has been implemented the ESS Readout core. So the Readout core now it's like a logic blocks inside the Sci-Compiler that can be just placed in the design, and the design becomes completely compatible from the point of view of the readout of the data, configuration, and timing distribution to the ESS. So all the works that has been done for Loki now is available for the instrument that officially will use the 5560, that are Miracle, Bifrost, CG Spec, and Vespa, and the other instruments that will be planned to be constructed in ASS and also in other facility like ISIS in the next feature. Obviously, this work can be done for any facility that require a customization to integrate our software and electronics inside the facility readout system. Okay, so the core the ASS core has been divided in 3 parts. The first part implement the readout. So it is possible using the custom packet to define a packet for Loki, Bifrost. Each one is very similar, but with some different packet structure. And the custom packet will automatically route the data on both Ethernet and ASS readout system. So it is still possible to read out data with Ethernet and also to be compatible with the ASS readout system. For the control, again, we have two sides, two ways to control at the same time any register in the register file of Sci-Compiler. Using the ASS front-end core, we have an AX interconnect in the design that connect the front-end electronics of ESS as a master to our register file, and also our AXI master control connected to the R5560 Ethernet has access via AXI interconnect to the Sci-Compiler register file. So, for example, it is possible to set a parameter or read out a parameter from both ESS control software and web interface or library in Python or directly from Sci-Compiler inside the firmware. You can see here a register file of the Loki firmware, and this is converted in multiple blocks or multiple registers inside the firmware, and this register can be accessed both from from web interface and from fast ESS readout. For the timestamp is reconstructed, started from synchronization signal and the reconstructed clock inside the front-end core or ESS front-end core. This timestamp is provided to the user firmware using an AXI stream, and in Sci-Compiler it appears like a standard blocks with a 55-bit output that is the timestamp. The firmware indeed just sample this timestamp and attach it to the packet that they send back to the ESS readout core as a form of event. This is a picture of the master module. The master module is the unit in the ESS backend that interact with the front-end electronics. So each master modules expose up to 12 interfaces. Each one can manage 16 front-end instrument. And inside this master module, we have a Virtex 7 FPGA. It collects all data, communicate via UDP and 100 gigabit per second in upstream Ethernet in upstream to the Kafka readout interface, and implements via a standard TCP/IP Ethernet the control and command interface. Some nice picture of the rack installed now on the Loki instruments at ESS. We have 5 of these racks installed to read out the experiment, and the next are coming. In October, during the last year, has been done several tests of the full electronics, so unit test and integration test at ISIS test beam. The first integration test has been done in EMMA. It was a partial test with the tubes on the beam connected to the preamplifier, connected to the R5560, that two R5560 that read out the detectors, a backend electronics, so a master module and a server, Kafka server, to collect the data. And it was successful because everything works fine. Then the experiment has been moved in a larger scale on Larmor, replacing the Larmor detector. Larmor is another SANS already present at ISIS, and a real scientific measurement has been taken to validate the system. So we can see here an image reconstructed by the full detector of Loki installed on Larmor. Several samples of different materials has been placed in front as samples in front of the detectors, and here some time of flight spectrum measured during the test beam. They appear very nice, and the scientists are happy, and they are see what they are expected. So we can see that the detector has been validated. In conclusion, Nuclear Instruments and Caen developed a new digitizer in collaboration with ESS and ISIS to cover all the requests of new detectors, neutron detectors, that will be installed in ESS and also in ISIS for the upgrade. The digitizer has a customizable firmware using Sci-Compiler. The Sci-Compilers allows directly the scientist involved in the construction and maintaining of the detector to maintain the firmware without the necessity of support that maybe can be not available in future years from internal resources of the facility. So this new firmware, new software really allows people without a deep knowledge of FPGA to implement, like we demonstrate, a large scale detector. Moreover, all the integration works that has been done to integrate the R5560 on the ASS indices, now it's an heritage for the other experiment that will benefit for free of the IP cores developed and all the validation that already has been done. So Miracle, Bifrost, CSPEC, and Vespa already we know that can be easy integrated in the facility without any other extra work and extra development. Loki is the first detector in ASS that has been commissioned, has been validated, and a full-scale model proof to be capable to produce relevant scientific data. Thank you.